In this video, we're going to discuss how we can solve for the steady state distribution by taking the limit as n goes to infinity of our P matrix, and we're going to pull out a value. Now, what I'm going to do is I'll just make up a Markov chain, and then in Octave, I'll show you how to do this. It's not something you can calculate or you can sort of solve for analytically like you used to in your calculus class. It's a little bit different. So let's start off by just creating a Markov chain. And, I'm just going to sort of add in some random numbers and hopefully I'll get it right. Okay, so I'll make this 1/2, 1/2. Oh, no. 1/4, 1/4, 2/3. I'll put a self-back loop here, 1/3, 3/4, 1/4, 5/6, and 1/6. Okay, so there goes our Markov chain. Why don't we go ahead and number the states? And as always, we can sort of make up our corresponding P transition matrix. Here we have 1/4, 1/2, 0, and 1/4. For state 2, we have 0, 1/3, 2/3, and 0, 1/6, 0, 0, 5/6, and finally for state 4, we have 1/4 and 3/4. No. At this stage, what we can verify very quickly is that, we have an aperiodic, positive recurrent and irreducible. Okay, so right off the bat, I can see 3 and 4 communicate with each other without a problem. From 3, I can get to 1 and 2 and 4 and get back to 3. So that basically now tells us, because I can do a loop between all these states, in fact, all the states communicate with each other, so they are irreducible. It's also aperiodic. You can kind of tell that just by the fact that we don't have any, if you ever have something like 1, that's a dead giveaway, but the other thing that sort of prevents it is this 1/3. Now, the way we'd want to check it is by taking P to some power. We'll do that next, but it definitely is aperiodic, and it also ends up being positive recurrent. So let's at least verify the aperiodic part, right? Because what happens is we can only apply this equation or use this technique if we satisfy these 3 properties. So our first step is just to verify that we are in fact aperiodic. So I'm going to type in the matrix here. Let's see what we get. So P equals 1 divided 4, 1 divided 2, 0, 1/4. Oops, and I should have put semicolons there. It's gonna barf, so let me, oh, it actually worked. It's surprising. Okay, I'm gonna type that in again. Really, you should be using semicolons. That's bad form not to. Okay. Okay, so I have my P matrix. Again, what we're going to want to do is check these diagonal elements to see if they oscillate, basically back and forth. There's a neat function in Octave where if you type in diag and then the matrix name, it will pull out the diagonals. So in fact, that's all we really care about. So we're going to check to see whether or not it's periodic. So here I have p to the 0. Now I have p to the squared, p to the third, p to the fourth, p to the fifth, p to the sixth. And so you can see there's definitely not a periodic, or else we'd see zeros pop up every now and again. All right, cool. Alrighty, so we're definitely aperiodic and we're positive recurrent. I'm not going to go through that. Again, we have ways of checking or calculating positive recurrence. Okay, so how do we actually perform this operation? Well, it's pretty easy. So one thing that we can do, so let's sort of look at this P matrix in Octave. So I have P. All right. This equation basically says we're going to take P to some very large number, right? It's going to go to infinity. What that sort of tells us is this matrix isn't going to blow up to infinity and it shouldn't go to 0. It's in fact going to converge to a number. So let's sort of watch that happen. So we have p to the 1. We can type in p to the 10th, right? Let's type in p to the 20. And what we should see here is p to the 10th looks pretty dang similar to p to the 20th. These two look very close to each other. And in fact, what we see are the terms converging. So here we have 0.5, here we have 0.7, here we have 0.718. And what you're going to see is these terms all converge. And not only that, the elements in each column are going to converge to the same value. So let's take p to the 50th. And look at that. Now we see all the same values in each of the columns. For good measure, this technique, if you want to do it numerically, you have to be careful about this power that you use. I would just consider you sort of just keep doing big numbers till it looks like it converges. Sometimes it might converge, let's say after 50, right? In this case, some will converge after 10. That's not the case here. You can sort of see different values. But if you start to see consistent values all the way down the columns, then this is converged. Usually what I like to do is just, let's say p to the 10,000. It almost takes no effort for Octave to do that. All right. So here goes our matrix that we get out. Okay. So p to the 10,000. And again, this sort of represents taking p to the some very large number. Okay. So at this stage, we said for this particular p, let's take the limit as n approaches infinity of p to the n. And let's see if I can actually paste this in. Cool. All right. Ooh, why can't I? Okay. So here goes p to the n, this matrix, as n goes to infinity. Now, what this equation is saying here, and actually this is for all j, it actually doesn't matter what row you're looking at, right? Because if you, again, look at what's going on here, every row is the same. All that matters is which column you're looking at, okay? So these are the different columns. Okay, who knows why this one? There we go. So here goes first column, second column, third column, fourth column. And what they're going to correspond to is the steady state or limiting probability for state 1, for state 2, for state 3, and state 4. And so this is going to give us pi 1, pi 2, pi 3, and pi 4. So if I ask you, okay, here goes some diagram or a probability transition matrix. What's the steady state distribution? Well, you take p to this very large value, and then you tell me, well, what are these values? Okay, so you'd say pi, and again, we're just going to give pi as a vector. We could give it as 1, 2, 3, 4 if we'd like, but we're going to give it as a vector. Pi is equal to 0.022, 0.472, 0.101, and 0.404. So what this tells us is that if we let our system run for a very long time, right, and we ask ourselves, well, what's the probability that x of n is equal to I, and we'll say as the limit as n goes to infinity, right? That's just given by pi, okay? That's pretty neat. The other way that we can think about it, yeah, actually, so that's probably the best way to think about it, all right? So this is why we call it a limiting probability. Now, the neat part about it is it doesn't matter where we start, okay? So again, normally we would use Pij to the n. So let's say, actually let's write this more formally. Let's say I wanted to calculate what is the probability that x of n is equal to j, given that I started at I. And normally what you would do is you'd say, let's take p to the nth power and pull out ij. Now, the interesting part here, again, if we choose any I, right, for the same j, we get the same value. What this tells us is it doesn't matter where we start out. The probability of where we end up at infinity time into the future, or far, far into the future, stays the same. And so that's why this distribution is very important. Okay? So it's independent of where we started. Now, that is only the case if we are aperiodic, positive recurrent, and irreducible.